Welcome! In this video, we will compare the energy behavior of constant air volume and variable air volume systems. Understand when and why each. The content of this video is divided in 4 pieces. First, the state path of a typical air distribution system for one zone. Second, the balances. Third, the typical summer dehumidification. And finally, how CAV and VAV set the supply state. Now that we have an overview of the content, let's go over the learning objectives of this video. By the end of this video, you will be able to define the air state points of a typical air distribution system for a single zone. You will also learn to apply mass, moisture, and energy balances to compute mixed air conditions and coil load. And finally, you will be able to explain how CAV versus VAV systems determine supply conditions at per load to meet sensible and latent requirements. But let's start with a question before we begin. I want you to think about the next question. Which property, this could be humidity ratio, enthalpy, or dry bulb temperature, dominates coil sizing in a hot, humid summer? Before we compute, recall that the coil axle is typically near saturation to handle the latent load. Therefore, the moisture removal requirement can control the required coil surface under living conditions. So think in terms of the energy balance and moisture balance. Outdoor air with high humidity ratio raises ventilation level load, which adds to the coil's job, even at moderate sensible conditions. As we hold some conditions fixed for comfort, it is often the reduction in humidity ratio, not just the drop in the temperature, that sets the coil living state, and therefore the coil load. So in the humid places, we are going to have to remove more latent load, no? Keep in mind that CAV and VAV share similar coil exit targets for dehumidification. So this means that the coil temperature in both systems are basically the same. But CAV may add reheat, while VAV reduces airflow. In both, if ventilation is significant, the latent part associated with humidity ratio can be the limited factor. So, to truly understand the energy flows in an HVAC system, we need a common language to describe the air at each point in its journey. Let's trace the Earth's state path through a typical system. So in this diagram, we just wait a minute. I'm going to put the laser pointer. In this diagram, we see 5 locations. We have here the ventilation air, the recirculation air, the mixed air, the coil exit, and finally the supply air that is after the reheating, and the air in the sun. So in this chart, we see the properties of air at each state. Here in this area, I think we can zoom here in this part. So you can here are the properties of each state. So that, and you notice that again, we have the ventilation air. Then in the mixture air, this is the air outside the coil. After the coil, this is the supply air, and this is the air in the sun, no? And then we have defined, as in previous cases, a fictitious air state X. And this fictitious state, it helps us to separate the sensible load from the latent load of the sun in our analysis. So for typical summer conditions, C is set by comfort at 24 degrees for the approximately 40% relative humidity, while C here is maintained the cold and air saturation. So this is in the question in the previous slide we were discussing. I was mentioning this part. The conditions of the coil are keep fixed because to take care of the latent load, and these temperatures are typically between 10 and 13 degrees Celsius to meet the latent load. These choices ensure that the supply can control temperature without allowing humidity drift high. We have to control the humidity. Outdoor air replaces exhaust, so A mixes with the return from E. We can see this here, and the coil then removes energy from E to reach the levels in C, and that's the exit of the coil. And after which S, that is the supply air, is set by the reheat. That is in this case, and it's more typical for the CAV system, or by airflow modulation in the case of the VAV. And this chain is this typical system will be the chain, the backbone of the framework for our analysis. And then now that we have defined that we can identify the Earth's state at each point along the path, the next step is to quantify what's happening. To do that, we'll use the fundamental principles of conservation, the mass, moisture, and energy balances. These equations are the bedrock of our analysis, allowing us to calculate the exact condition of the air and the loads on the system. So for the conservation of mass and moisture, so we compute the mixed air here. That is, let's use again the pointer. So we see that the mixed air, because we have conservation of mass, is going to be the sum of the outdoor air and the return air. And then we also have the same for the moisture. Then next we apply the energy conservation. So in the energy conservation, once again, we have for the mixed air, we multiply each term by their enthalpies. And in the case of the coil, the heat that removed from the coil, and we see that is the enthalpy difference between the enter and the exit. And finally, we close with the sound system balance. It's in the form of this Q of the coil. So this is the sensible load, the latent load, plus the heat from that is given to the air, plus the mass volume of the air entering, and the enthalpy difference between the state A and state C. So this compact expression actually aggregates sensible, latent, reheat, and ventilation effects, and is our diagnostic for the power load decisions. In building on our understanding of the energy balances, let's now see how these principles apply to a critical aspect of HVAC design, that is latent control, particularly during summer. We were discussing this during the question. We'll explore why the cooling coil's function goes beyond just chilling the air and is key to maintain a comfortable humidity level. The air exits the coil, so at state C, as I mentioned, is near saturation, typically between 10 and 13 degrees, and this ensures the moisture removal to hold the humidity ratio in the sun. In this choice protects the humidity even when sensible loads are light. In Humid climates, ventilation contribute to a large latent load. This is actually answering the question. The latent load of in humid climates is big. It can even dominate. It can dominate the load in the coil. So we have that the term here is the mass flow in the outdoor air and the difference of enthalpy between the and the ventilation air and the sun air. This can be significant because the enthalpy of the ventilation air, this one here, includes both temperature and moisture effects. So the latent load, this is why this term is big, because here we have a sensible load in this enthalpy plus the latent load in a humid place. It's big, it can be big, so it increases, So that's the latent load requirements often set the coil exit. This is answering the question of the third slide. Then once the coil exit properties C are fixed by latent control, the sensible requirement is met by setting the supply air properties at S. When we keep C fixed because of the latent load, but this can be too cold for the sun, especially moments when the sensible load in the sun are low. And then we need the reheat to adjust this the state at S, so it's appropriate for our sun. This is an CAV system, no? We use the reheat. In the VAV, we do this by changing the mass flow, So we reduce the mass flow so that S can be approximately C, and then the reheat is avoided until the minimum flow limit. So this means that in the VAV, what we do, we variate the flow to get this state at S that is proper for the sun, and then we are going to need at some point that the flow is going to reduce until we cannot reduce anymore the flow, because we need to keep a good indoor air quality. So at that moment, what is going to happen? We are going to need reheat, because if we cannot go below the minimum flow, and then the sensible load at the sun is low, so we are going to start to cool the sun over what we want. It's going to be colder and colder, so we don't want that. So what we do is we apply reheat at the VAV system. So now that we see how the coil is set to handle latent loads, let's explore how the air moves from the coil to the sun and how the final supply condition is determined. This is where the fundamental difference between CAV and VAV systems becomes most apparent, as they use entirely different strategies to meet some sensible load. This is a little bit of what I was talking before. So in CAV, the airflow is fixed, so we reheat to match the sensible need. This yields excellent temperature control, but incurs in the need of introducing heat to and at part load. This way of working of the CAV using reheat, it also allows us to have a good temperature control. In VAV, we modulate the airflow to track sensible load while keeping the coil exit at C cold enough for latent load control. This is what I was explaining. You just, if you need more or less air entering the sun, you just increase or reduce the flow. So reheat is withheld until the minimum circulation ventilation constraint forces. Thus the fan and the coil energy fall with load. So because you are going to be giving less and less air mass flow to the sun as the sensible load of the sun decreases, the fan is going to be the fan and the coil energy is going to be falling. So practically at every light loads, verify minimum flow to maintain mixing and avoid the stagnant air. What I was saying is, if you start to reduce the mass flow, you have to keep in mind the indoor environmental quality. You cannot go until 0, for example. When the flow hits this lower limit, reheat may be introduced to preserve comfort while still meeting indoor air quality. Okay, to conclude, let's summarize the key takeaways from our discussion. This slide distills the core concepts and the framework we used into 3 essential points that you should remember. First, the key takeaway is the state balance framework. This with A, E, C, S, C defined and balances applied. You obtain mixed conditions, coil duties, and supply targets consistently. And then, in hot or humid conditions, latent needs often fix C, and the ventilation may be the largest latent driver. Recognizing this early prevents undersizing and poor humidity control. Finally, CAV and VAV diverge at the supply decisions. CAV uses reheat at constant flow. VAV uses variable flow with minimal reheat until a minimum flow limit. This explains these energy differences. To conclude our discussion, let's look at some key concepts that belong to what we learned, offering ways to continue learning about HVAC optimizations. And I invite you to continue learning about HVAC and looking at these concepts. So to deepen your toolkit, study coil bypass factor and apparatus viewpoint. These concepts refine how we choose the coil exit to achieve that dehumidification without excessive energy use. You could also explore economizers and mixing strategies. This is to use outdoor air fraction to lower the enthalpy of the air mix. And finally, investigate dual path DOA systems where ventilation is cool and dehumidified on a separate path. This approach directly addresses latent loads and can reduce circulation, airflow, and fan power in many applications. So thank you for watching this video and continue your learning journey in HVAC systems.